All right, today we're going to be learning a different way of integration. And up to this point, most of the integrals that you've had to integrate were pretty simple. You could use the power rule or just look at the table of integrals and get the antiderivative. But today we're going to learn a technique that is extremely important. It's probably the most common technique of integration for integrals that are a little bit more involved, and it's called the U substitution. And essentially the idea, we're going to do several problems, but essentially the idea is that you want to choose a substitution for u. So what basically you're going to do, you're going to let u equal some part of the function. And after you do a few of these, you'll see it's not that bad, but you want to take the derivative of that, and you want to think to yourself, what could I let u equal so that when I take the derivative of it, it will cancel out something else that is in the function. All right, so we're going to do 4 examples here in this first problem. All right, in this first problem, we are integrating the function x squared plus 1 squared x dx. And so, once again, the first question you want to ask yourself is, what could I let u equal so that when I take the derivative of it, it would cancel out something else? Well, you've got a couple options. If you let u equal x, when you take the derivative, you just get dx, or 1 dx. Now, that doesn't cancel out x squared plus 1 at all, so that's not going to get us anywhere. You could also let u equal x squared plus 1 squared. And you could let it equal that, but that's not going to work either, because if you take the chain rule, it's going to get kind of messy here. So we don't want to let u equal either one of those options. What you really want to do is you want to let u actually equal just x squared plus 1. Now watch how this works. If you take the derivative of that, you get 2x dx. And you solve this for dx, so it's going to be du over 2x equals dx. Now you're going to replace back here in the original function, you're going to write your integral now in terms of u. So your integral is going to be u squared, because x squared plus 1 is u, times x. And in dx, we're going to replace with du over 2x. And you can see here that the x's are going to cancel. And you also see here that you have this 2 there. I'm going to move that outside the integral so that it ends up being 1/2 the integral of u squared du. And now let's continue that over here. So then now you'll have 1/2 straight line u cubed over 3. And so now you go back and replace your u with x's, and so you're going to have x squared plus 1 cubed over 6. And you also need a plus c here because we are not integrating, we don't have an upper or lower limit, so this is called an indefinite integral, and so anytime you have that, you need to have a plus c afterwards. And that is the answer to example 1a. All right, the next example, we have the integral of sine squared 3x cosine of 3x dx. Now, once again, we've got a couple choices. The question is, should I let u equal sine of 3x, or should I let u equal cosine of 3x? Well, you can see that if you let u equal cosine of 3x, you take the derivative, and you're going to end up getting -3 sine of 3x. And that doesn't cancel out both sine squared 3x, so that's not going to get us anywhere. So we don't want to let u equal cosine of 3x. Instead, we're going to let u equal sine of 3x, and you're going to see how this works in just a moment. So we're going to take the derivative, as we did in the last problem, and the derivative of sine is cosine, but don't forget that we have a chain rule situation, so 3x is inside sine, so we're going to need to multiply by the derivative of 3x. This is going to end up being 3 cosine of 3x dx. And now we're going to solve it for dx, so it's going to be du over 3 cosine of 3x equals dx. And now we're going to replace our dx and actually turn the whole thing into u's. So this is going to end up being the integral of u squared times cosine of 3x times dx, which is defined as du over 3 cosine of 3x. And now we can cancel off the cosine of 3x's, and we can also pull the 3 out in front of the integral and make it 1/3. So it's going to be 1/3 the integral of u squared du. So now we're going to integrate just like we normally would, except we're integrating with respect to u and not x. So that's going to be 1/3 the integral u cubed over 3. Now that we've integrated, we're going to replace our u with sine of 3x, and so our final answer is going to be sine cubed of 3x over 9. And don't forget, we need a plus c on all indefinite integrals, and that is the answer to this one. Alright, at this point I would encourage you to stop the video and try letters C and D on your own and see if you get the same answer that we're going to get here. Alright, so letter C is the integral of x squared over 16 minus x cubed squared dx. Alright, so you can pretty much see what we need to let u equal here. We're going to let u equal 16 minus x cubed. Why? Because if we take the derivative of this, the derivative of 16 goes away and we end up getting negative 3x squared dx. And you can see here that this is the key, x squared, x squared. And after a while your eyes will start to recognize that and you'll see what to let u equal for each problem. So we're now going to divide by negative 3x squared, so du is du over negative 3x squared equals dx. Okay, so now we're going to go back and we're going to write everything in terms of u. So this is going to be the integral of x squared over u squared times dx, which is du over negative 3x squared. And once again, you see the x squareds cancel. And we have this negative 3, so I'm going to bring that outside of the integral, and that's going to be negative 1/3 the integral of 1 over u squared du. And then I'm going to rewrite that as negative 1/3 the integral of u to the negative 2 du, and that way I can use the power rule. So I'm going to add 1 to the power, and then I'm going to divide. So my integral is going to be negative 1/3 straight line u to the negative first divided by negative 1. And then we can also see here that the negatives are going to cancel and make those both positives. And I'm going to move the u back down, so this is going to end up giving us 1 over 3 u. And we know that u is 16 minus x cubed, so our final answer is going to be 1 over 3 times 16 minus x cubed plus c. And that is the integral. Alright, next example, we have the integral of 3x squared times the square root of x cubed plus 2. Alright, so you can see that we should let u equal x cubed plus 2. So that when we take its derivative, you get 3x squared dx. Divide once again by 3x squared, and you get dx. So now we are going to rewrite our integral in terms of u. So this is going to be 3x squared times the square root of u times dx, which is defined as du over 3x squared. And hey, this is pretty convenient because the entire 3x squared cancels, and we are left simply with the integral of the square root of u, which, how about we write that as u to the 1/2 power, u to the 1/2 power du. And so now we're going to integrate that, and we end up getting u to the 3/2 divided by 3/2, which is the same as multiplying by 2/3. And so now we can plug our u back in, and our final answer is going to be 2/3 u, which is x cubed plus 2 to the 3/2 power plus a constant. And that is our final answer to that one. Alright, in this next example, we're going to do a u substitution. However, you're going to see in this example that when you do it, it doesn't work, and so you have to do an extra step. And for some of these integrals, you just have to get really creative and think about different ways to solve them. So let us see how we're going to do this one. So we are given the integral of x square root of 2x minus 1 dx. So if we just start working this problem, your initial instinct may be, well, I'll just let u equal 2x minus 1. And you start taking the derivative and you get 2 dx. And you solve it for dx, and you get du over 2 is equal to dx. And you get stuck because now you go back and you rewrite your integral, so it's going to be x times the square root of u and du over 2, and you're like, oh no, nothing cancels. I still have two variables. I have an x and a u, and that's not going to work. However, what you can do is you can go back to your u substitution and you can solve it for x. So let's go ahead and do that. If we solve it for x, we're going to get u plus 1 over 2 equals x. So actually what we're going to do is we're going to take this and we're going to plug it in for that x. And then we'll get something that we can integrate with all u's. Alright, so let's see how this works. We're going to have the integral of u plus 1 over 2 times the square root of u and du over 2. Alright, so I'm going to pull the 2 times 2 out, and I'm going to make that 1/4. So it's going to be 1/4 the integral of u plus 1 times u to the 1/2 du. And maybe I'll go and continue this up here. So now I'm going to distribute the u to the 1/2 in there, and so I'm going to have 1/4 the integral of u to the 3/2 plus u to the 1/2 du. And when I integrate this, I'm going to get 1/4 2/5 u to the 5/2, and then I'm going to get 2/3 u to the 3/2, and now I can plug in my u, and so we end up getting 1/4 times 2/5 u, which is 2x minus 1 to the 5/2 plus 2/3 2x minus 1, run out of space, to the 3/2 power. And if you tack on a plus c, that will be your final answer to this problem. Alright, so this next example is similar to the last one. So we're going to have the integral, only this is a definite integral because we have a lower and upper limit. So we're going to have to plug those in at the end. So it's going to be 1 to 5 x over the square root of 2x minus 1 dx. So once again, we're going to let u equal 2x minus 1, and you'll let du equal 2 dx. And so du over 2 is going to equal dx. And so now we will replace, and so we have the integral from 1 to 5 of x over the square root of u times du over 2. So now we are going to pull the 1/2 out front, rewrite our integral, and we're going to replace x with that same thing that we did before, which is going to be u plus 1 over 2 divided by the square root of u. And if I multiply the top and bottom here by 2, see that the 2's cancel there, and this 2 will combine with that 2 out there and make 1/4. So essentially we're going to have 1/4 the integral of 1 to 5 of u plus 1 over u to the 1/2 power du. And now what I'm going to do is I'm going to divide this u to the 1/2 into both u and 1 so I can break it up. And so I get 1/4 integral from 1 to 5 of u to the 1/2 plus u to the negative 1/2 du. And now I'm going to integrate, so that's going to equal 1/4 the integral from 1 to 5 of u, so it'll be 2/3 u to the 3/2 power, and then it's going to be plus 2 u to the 1/2 power, and then I'm going to plug u back in as 2x minus 1, so this is going to be 1/4, and put a bracket and we'll say 1 to 5, and this is going to be 2/3 parentheses 2x minus 1 to the 3/2 plus 2 times 2x minus 1 to the 1/2. And now I'm going to plug in my upper limit of 5. So when I plug 5 into here, I get 9. All right, and so at this point you want to you have basically two options. You have 9 to the 3/2 power. So you can either write that as 9 to the 1/2 raised to the 3rd, or you can write it as 9 to the 3rd raised to the 1/2. And obviously it's easier to take the square root of 9 and cube it than it is to cube 9 and then take the square root. So we're going to rewrite it that way. All right, so since you have that, I'm going to erase that. All right, so what do we have here? We have 2/3 times 9 to the 1/2 cubed plus 2 times 9 to the 1/2 power. And so this is going to be 27 times 2, that's going to be 54 over 3, plus the square root of 9 is 3, times 2 is 6, and 6 I'm going to write as 18 over 3, and so I end up getting 72 over 3, all right, which is 24. And so our upper limit of 5 gives us 24. So essentially what do we have here? We have 1/4, and then our upper limit is 24 minus our lower limit. When we plug in 1, let's go all the way back here, and we plug in 1 here. It's going to be 2 times 1, it's 2 minus 1, which is 1. 1 to any power is 1, so that's going to give us 2/3. And over here, same situation, plus 2. And 2 I'm going to write as 6/3. So that's going to give us 8/3. So this is going to be 24 minus 8/3. And I guess I should have left this as 72 over 3. So we're going to have 1/4 times 72 over 3 minus 8, which is 64 over 3. And 1/4 goes into 64, so these two right here can give me 16 over 3, and that should be the final answer here. All right, a few more examples here, and these can be a little complicated, so we're going to take them slow, step by step, and see if we can figure these out. All right, in this first example, we have the integral from 0 to pi over 3, And for the sake of laziness, I'm going to leave the 0 to pi over 3 off for the entire problem until we get to the end where we need to plug it in. So essentially what we have here is sine of x plus cosine of x squared. And it tells us to do this by expanding. So we're going to FOIL this out. Please don't make the mistake of squaring sine of x and cosine of x. You actually have to FOIL it. So if you FOIL it, you're going to get sine squared of x plus 2 sine x cosine x plus cosine squared of x. All right, and we remember from pre-cal, from trig, that sine squared plus cosine squared is simply 1. So this is going to be the integral of 1 plus 2 sine x cosine x dx. All right, and so we want to break this up, and when you see this plus sign in between two functions, you can use the property of integrals where you can break it up into two different integrals. So this is going to be the integral of 1 dx plus the integral of, and I'm going to pull the 2 out and make it sine of x cosine x dx. All right, so the integral of 1 is simply x. All right, so and that's going to be evaluated from 0 to pi over 3. And then this one here is going to require us to do a u substitution. All right, so we'll put this one on the back burner for just a moment. Actually, no, let's go ahead and just figure out what that is. So if you plug in pi over 3 minus 0, that just gives us pi over 3 as that particular part of your integral. All right, so now if we go over here, we're going to let u equal, well, we have a choice, but I'm just going to let u equal sine of x. And so now when we take the derivative, we get du is equal to cosine of x dx. And so du over cosine of x equals dx. And now we can go ahead and plug that in. So we have 2 times the integral of u, actually. So u is sine of x times cosine of x times du over cosine of x. And once again, that's the whole point of the u substitution. They will cancel, and you end up getting 2 times the integral of u du. And we're going to use the power rule, so that's going to end up giving us 2u squared over 2. And u is sine of x, and so actually the 2's are going to cancel there. So this end up giving us sine squared of x. And don't forget, we have to evaluate that at 0 and pi over 3. And so if we plug in pi over 3, that is 60 degrees, and the sine of 60 is root 3 over 2. So if we square root 3 over 2 minus the sine of 0 is 0, so 0 squared is just 0. So if we square this, we're going to get 3/4. But don't forget that way back here, we had that part as well. All right, so it's going to end up being, final answer, pi over 3 plus 3/4. All right, this next example is going to be the integral of 2 over x squared minus 6x plus 10 dx. All right, so this one, it says to use the technique of completing the square on the denominator. This one's kind of a weird one because it's not quite obvious exactly what to do when you look at it as far as how you would integrate this. But let's see what we get. If we integrate this by completing the square, let's just review real quick completing the square. Let's do a separate problem over here. Let's say we have x squared minus 10x plus 4. The basic idea is you take half of that and square it. So you're going to have x squared minus 10x, take half of 10, which is 5, and square it, so that's 25. And then you can't just add 25 without subtracting it back out as well. So it's going to really be plus 4 but minus a 25. And you have to subtract it out because you need to balance it. So that way you can factor that. And that's going to end up being x minus 5 squared minus 21. And notice that when you complete the square, this number is always going to be half of that number. So you don't have to think very hard whenever you get to this step here where you're trying to factor it. It's always going to be half of that number. All right. So that is a review of completing the square. So I'm going to erase all of that and go back to our problem. So for our problem, we have x squared minus 6x plus 10 on the bottom. So if we're going to complete the square there, we need to actually take half of 6, which is 3. So we're going to say x squared minus 6x. Half of 6 is 3. Square that is 9. And we need a plus 10 here, and we're going to subtract a 9 back out to balance it. And so we're going to have 2 over, and I'm going to factor this, but I just gave you a shortcut. When you factor that, it's always going to be x plus or minus half of the middle term. And 10 minus 1 is 1. Alright, so now we're going to do a u substitution, and we're going to let u equal x minus 3. So then now we take du is equal to dx, and by the way I need a dx right there. So this is going to end up being the integral of 2 over u squared plus 1 du. And some of you can probably see where this is going. I'm going to take the 2 out in front of the integral, and I get 1 over u squared plus 1. Alright, so you can kind of see that, okay, I've seen this before somewhere. The integral of 1 over u squared plus 1 is the inverse tangent. So this is going to end up being 2 times the inverse tangent of u. And now we can plug u back in. So u is x minus 3. So our final answer is going to be 2 times the inverse tangent of x minus 3. And because it's an indefinite integral, we need a plus c at the end. Alright, hang in there guys. Just a couple more examples here. And example 8, it's telling us to integrate this by separating the bottom, dividing the bottom into both things on the top. So basically we have this integral where it's 3x plus 2 is your numerator, and your denominator is going to be the square root of 1 minus x squared dx. Alright, so if we take the denominator and divide it into both parts on the numerator, we're actually going to have two different integrals. 3x over the square root of 1 minus x squared plus the integral of 2 over the square root of 1 minus x squared dx. And we need a dx there as well. Alright, so let's just integrate the left one, and you can see that we're going to need a u substitution there. So we're going to let u equal 1 minus x squared. So that way du is going to equal negative 2x dx. And we're going to divide by negative 2x. So du over negative 2x equals dx. And we're going to now go back in and plug everything in. So it's going to be 3x over the square root of u times dx, which is du over negative 2x. And as we've seen several times, the x is going to cancel. And the 3 over negative 2, I'm going to bring that outside the integral. And so that's going to be negative 3 halves, the integral of 1 over, tell you what, I'm just going to write that as u to the negative 1 half du. And if we integrate that, that's going to give us negative 3 halves. And that's going to, if we add 1 to the power, it's going to end up giving you positive 1 half. And then you divide by positive 1 half, which is the same as multiplying by 2. So that's going to cancel off those 2's right there. And it's going to end up being negative 3 times u to the 1/2. And that's the same as the square root of 1 minus x squared. All right, but don't forget, we have this second integral over here that we haven't dealt with. That's going to be pretty easy because if you take the 2 out in front of the integral, you can see it's just going to be 1 over the square root of 1 minus x squared dx. And you may recognize that as the inverse sine of x. And so that's just going to be basically 2 times the inverse sine of x. So we're going to add that over here to our answer that we got from the other one, 2 inverse sine of x plus a constant. And that is our answer to that problem. All right, this example 9, we have the integral of 1 over 4 plus 16x squared dx. And it says we need to use the table of integrals in order to get this integral. So if you actually look at the table of integrals that I gave you, number 17 at the bottom, there is an integral property there where it says the integral of du over a squared plus u squared d, not d, is actually equal to 1 over a inverse tangent of u over a plus c. So we're going to use that integral in order to do this problem. So do you see here that you need to get this integral here in terms of u, because that's the only way you can use this property over here. So we're going to let u equal 4x. And you can see that u is simply the thing that is being squared, so 16x squared, so 4x is being squared. So du is equal to 4 dx, and so we can rewrite this integral as the integral of 1 over 4 plus u squared, and we actually need to solve this for dx, so du over 4 equals dx. So dx is going to be du over 4. And this right here is a step that a lot of students will forget. They'll try to go straight from here to here and use the formula without going through this process here, and their answer is going to end up being off by a factor of 1/4. So make sure you get everything in terms of u. So we're going to pull out the 1/4 here, and we have an integral 1 over 4 plus u squared du. And now we have basically it matched up exactly with what's on the table of integrals. And so now we can basically match it up. And you can see that a is simply the square root of the constant that's being squared, and u is the square root of this. So we end up having 1/4 times 1 over 2 inverse tangent of u, which we'll just go back and plug in u, which is 4x, over a, and a was 2. And so then now when we cancel these out, that's going to be 2x. And so we can actually multiply the 1/4 and the 2 in there. So our final answer is going to be 1/8 inverse tangent of 2x plus a constant. And that is the answer to that one. Alright, this is the last example that we're going to do on u substitution and other algebraic techniques. And just to kind of give you an idea here, basically what you're doing is you're putting a bunch of tools in your tool belt so that anytime you have an integral, you can complete the square, you can do u substitution, you can break it up into two different integrals by dividing the bottom into both pieces on the top. So you've got a lot of different options. All right, so this last one is, it says we need to use the method of completing the square on the bottom, in order to do this one. So we're going to end up with the integral of 1 over the square root of negative x squared plus 4x minus 3. Alright, so there is times dx. Alright, so you can't complete the square until you get this leading coefficient to be positive. So what you're going to need to do is you're going to have to factor out a negative 1 from inside the square root. So basically what you're going to have is the square root of negative 1, and then if you factor out a negative 1, all the signs are going to change. So that's going to be x squared minus 4x plus 3. And I'm going to leave a space right here because we're going to complete the square. So I'm going to put the plus 3 right there. Alright, so completing the square, we need to take half of that, which is negative 2, and square it. So that's going to give us a plus 4. And we also need to subtract a 4 so we can balance it out. And then we're going to factor that, and we get 1 over the square root of negative 1 x minus 2, and I'll put another set of parentheses on that, squared. And then 3 minus 4 is negative 1. Alright, and now I'm going to distribute the negative 1 back into the parentheses. So that's going to give us 1 over the square root of 1 minus parentheses x minus 2 squared dx. Alright, and so now we are going to apply the property 16 on your integrals and derivatives sheet, which says the integral of du over the square root of a squared minus u squared is equal to the inverse sine of u over a plus a constant. Alright, so essentially here this is, and 16 and 17 really are the main ones that you're going to need to memorize for the AP exam. Alright, 16 and 17. Let me write that there so you'll know. Those are the two main inverse trig integrals that you need to have memorized. So we're going to let u equal x minus 2. So du is equal to dx, so that's pretty simple. So now we can go ahead and replace everything and put it in terms of u. So it's going to be 1 over the square root of 1 minus u squared, and dx we can replace with du. And so our a is simply 1. You have to watch for that because if this was, say, 9, a would be 3. Alright, so we can write our final answer as the inverse sine of u, which we called earlier to be x minus 2. So it's going to be x minus 2 over a, which is 1. So it's just going to be x minus 2 plus a constant. And that is the end of this extremely long video. Alright, we will practice tomorrow more of these techniques in class.